In Rust, if you try to use a variable inside a thread, the compiler stops you, and then it tells you to add one keyword, which is move. But why? What is Rust protecting you from? So let's look at this example where we have thread spawning and we are passing let or we are just printing a variable s in our thread. It looks fine and it's very simple, right? Just printing a string inside a thread. But Rust will not compile this. Actually, it's giving an error right now, which is that to take ownership of s, we have to use move keyword so that we can pass our ownership to our thread. Here's what's actually happening behind the scenes. The closure is borrowing our variable s. The thread runs independently. It might run after main ends. So what if main ends and thread is still using our variable s? So that's what we call dangling reference memory that no longer exists. Rust stops you at compile time and says I cannot guarantee this reference will be valid. To fix this, we are going to use new keyword. This one keyword changes everything. Move takes ownership of our variable s and it moves it into the thread. Now thread is the owner. The thread no longer depends on main. Think of it like this: without move, we are just borrowing a book. With move, we are taking the permanent ownership of our book. You cannot destroy the library if the book is still borrowed. Rust is strict because threads are dangerous. In other languages, you can accidentally access freed memory, create data races, and it's going to be crash at runtime. Rust eliminates these problems at compile time. Move does not always mean copying. For string like dynamic data types, ownership is move. And for simple types like sign bit integers and send bit integers, simple values like that, only copy will happens. Here x is so so another thing I like to add here is after passing new keyword and passing our variable s, we cannot use our variable again. So let's look at that. So as you can see, we are getting a compile time error because we have already passed on ownership to our thread. So now let's look at how how we pass simple uh, data types in our thread. So let's take number 5. So as you can see, uh, simple data type like uh, sign 32-bit integers. There's no ownership issue here because this data type is stored in the stack, not in the heap. So Rust actually forces you to choose share safely or transfer the ownership. That's how Rust prevents data races before your code even runs. In most languages, threads are powerful but dangerous. In Rust, threads are powerful because they are restricted to into safety. So yeah, that's it for this video. Thank you.